from EDAG. I would like to talk a bit about our Center of Competence for Virtual Function Development. So first of all, what I would like to talk about in a short agenda. First of all, I will present myself, that you know who is this person, who is this guy who is standing in front of you and is talking about virtual function development. Second topic, I will shortly introduce you to the company EDAG, what we are doing, where do we come from. After that, I would like to answer the question, why is virtual vehicle development so important and is getting even more important in the future. Apart from that, we have a detailed look about how does the virtual development come starting from the concept phase to the start of production phase. How does this fit together? How do we work there? And as point 5 and 6, I would like to present you 2 examples what we are typically doing in our Center of Competence. First of all, I would like to introduce you to a new Excel concept we have developed, and point 6 is about more something like you are doing here. It's more in high performance and motorsport vehicles, and I would like to show you what we are doing there. So first of all, about myself, I'm Felix Merkner. I'm working at EDAG since around 5 years now. I'm working there as an expert simulation engineer and also as the Center of Competence leader for virtual function development. I've studied at the Hochschule in Esslingen. I was also there in the ESTAL Esslingen 3 years in the Formula student team as leader for suspension systems. And after my experience in Formula student and after my my ending of my bachelor study, I was coming to EDAG and working there as first of all a development engineer and then coming the expert simulation engineer I am now. Most of the thing I'm doing is, or where I come from, is multi-body simulation, but I also get more experience in full vehicle simulation, and that's also why I'm now here as the Center of Competence leader for virtual function development. So maybe if you don't already heard about EDAG, maybe some words about what we are doing in the company EDAG. We are here since 1969 and have a lot of offices around the world, about 60 locations worldwide. We are in 19 countries, so Germany is the main country where we are sitting. Most of our employers are there, but we have also some offices like a very new one in Austria, in Steyr, but also, for example, in Spain, Great Britain, but also like in China, India, or in the USA. We are quite a lot of employees, around 9,000 right now. And as an engineering service supplier, we don't have our own products, but we like to show what we can do and what our technical knowledge is by building and developing show cars, like our CityBot or other cars where we show what we are familiar with and what our technology is. So what are we doing? The EDAG is, we say we are able to make a 360 degrees of vehicle engineering. That means that we can, from a white paper until series of production, can develop a complete vehicle by our own. So we have 4 sections. The first of all, the vehicle engineering on the upper left, where we all comes together, which we need for developing a vehicle or car, something in the automotive sector. So we have the body and white department, we have suspensions, we have styling and design and all things like that, all in the vehicle engineering department. Then we have our electronics. As the name already says, this is more about everything which has something to do with electric and electronics, but also autonomous driving systems, functionality, safety, cybersecurity, everything is included in this department. The third one is production solutions. So this means we are, as a service provider, we don't making our own products, but we are able to help our customers to develop their production solutions. It means if you, for example, we have a new customer who wants to build a vehicle, we can not only develop the vehicle, we can also help to develop the factory, and how this should look like, that he can produce his own cars. Last but not least, we have on the lower left the software and digitalization, where we have some ideas like smart cities, smart factories, and the mobility software included there. So my department is the vehicle dynamic department. Most of the vehicle dynamic department is sitting in Germany, as you can see here. What we are doing are the specific subsystems, what we are seeing here. So we are responsible for the axle system, but also for steering, vertical dynamics, brake system, wheels and tires, and the driving dynamics. And if we have a detailed look, especially in the future where we have more steer-by-wire things and stuff like that, we are also getting in this vehicle motion sector, which comes all together, where the vehicle dynamics and the electronics comes all together in the vehicle motion system. So that's it for a short overview about the EDAG. So now I would like to answer the question, why is virtual development so important today and becomes even more important in the future? So I have a quote for you. I got this from a YouTube video from the Mercedes AMG Petronas Formula 1 team simulator driver. And he said in 9 out of 10 vehicle setups they are doing after the second training of a Formula 1 event, the result which comes from this simulator drivers is better and is used on Saturday for the qualification rounds than they have done it on the proving ground or on the racetrack. So I think this is already something where we can see how good already a virtual development can be. Yeah, we are in a very high performance sector. We are in the motorsport, and this quote already says, okay, we are so good that 9 out of 10 times we are even better and can do more than they do on the track. But how does this look like in a typical vehicle development process? So what I've bring here is a normalized development process. We are starting with a project kickoff. We're having a first framing benchmark phase. Probably this is where we start building up the first suspension models. Then we have the concept phase. Maybe there's already a full vehicle MBS model. And then we have our design freeze. At the design freeze, there's coming right now the first hardware phase. So probably you get a component car, very simple, where you just put in some suspension things, powertrain, maybe also already a battery system or something, where you can test your subsystems. Yeah, but it's not the full vehicle, it will be in the future. This will come with the first prototype phase, where you have a first hardware prototype phase of your future vehicle. Most of the time you have a second prototype phase, maybe also a third one, depends on the OEM or on the company. And after all, you have your start of production vehicle, which should be the one which you will sell in the future. But what will happen in future now? So all of these phases will probably be deleted. We don't need any hardware anymore. How will this look like? So we have the same phases here, but now we don't need any hardware anymore. The only hardware we will need is at the start of production. Everything else can be done virtual. So looking about the design freeze where we had our first hardware, we don't need it anymore. What we are doing is we build our virtual model and going on a simulator. Yeah? And step by step we can just delete all these hardware phases because we can do everything on our simulators. We can make the control systems, we can make the applications, everything on a simulator, and at the end we only need one hardware right now to get the validations and homologations done, which can already also be done virtual, and this is how the future could look like. Maybe just a short example. So we have a short video here where we are driving, for example, an IBG car maker vehicle. So this can already done in a very early phase. This is an example car, but maybe you can already start right after the kickoff phase with a build-up of a virtual twin, and you can directly drive an example car and test it and look like the behavior is. So in the end we can say there will be less hardware, close to none hardware phases, and more virtual prototypes. Maybe another example regarding some testing on a track versus a day in a simulation office. So their daily work, you're starting 8 o'clock on the proving ground. You're starting with your first tests with a setup you have evaluated. Then you're going back, had some maneuvers driven, like a constant radius cornering, I don't know, step steer, what else. And you go back when you choose a second setup, I don't know, remove the dampers, or remove the springs, use different spring setups, go back to the proving ground again, drive your same maneuvers, I don't know. In the end of the day, I don't know, maybe you had the opportunity to drive 4 to 5 setups for the day, because it takes always a long time regarding changing any kind of setup like the dampers or the springs. So how does the work for a simulator looks like? Yeah, he's also starting his day 8 o'clock in the office. It's not, oh, come on. If it's raining or not, I don't care. For this one, if it's raining, he can't do his work. For me, as in the office, I don't care. So starting my work at 8:15, I can directly start automatically 150 handling simulations with all these maneuvers I would like, with 150 different setups. In the end of the day, I can automatically evaluate all these simulations. So by the end of the day, I have evaluated about, for example, 150 different setups with the same handling maneuvers the test drive on the proving ground would have been driven. What else is a positive thing about the virtual development? One thing is that we can also directly implement it in our V model. So we have the different levels here from 0 to 4, and with the virtual development, we are most of the time here in the level 1 and level 2, so we are in the vehicle and the system level. And we can directly go into this for virtual development and start right at the beginning of a vehicle development process. So for example, if we want to develop any kind of feature for our vehicle, like an assistant lane changer, probably most of the time if I want to test it in hardware, I need a vehicle where I can test it. But in virtual development, I can just use any kind of virtual vehicle, get my code, and doing this kind of process, and already start to evaluate and to applicate my software I have written before I have to wait for any kind of hardware phases. So all this together, what do we have or what are we doing especially in our Center of Competence Virtual Function Development? So first of all, we have our multi-body simulation in there, and the second one, but I think the most important topic if we are talking about virtual development, is correlation and validation. Yeah? The models you have and the outcome you get is only as good as your validation is. Yeah? If you have a virtual model that isn't comparable to your real car, you don't get any kind of output from that. We are also doing some tool development in our Center of Competence, and we are also able to do, for example, sensitivity and tolerance analysis. We have our own plugin developed for that. We are also able to make some virtual attribute development. Some other topics are like, for example, ADAS and driving function development, which is also possible for us to do. Then we have the driving dynamic evaluation, the automatization of all of these kind of simulation and analysis, and by the end we are also doing things in the direction of high performance or motorsport with the driving dynamics performance optimization. So why do we have to bundle all these competences? I have bring you two examples. You can see maybe what is going wrong. So I don't know if someone is familiar with Adam's car. So this is something typically in the beginning of building up our models. It doesn't work like it should be. And that's why we said, okay, we have to bundle our competences, but something like that will not happen anymore. So let's have a detailed look in how we are working regarding a full vehicle development from a concept phase until the start of production. So first of all, we have our multi-body simulation model. We have two sides. We have one side which is more for the handling, and we have our second model which is more for ride and comfort behavior. So first of all, starting with a handling model, you will probably start with defining your hard points, defining your kinematics, first initial damper curves and stuff like that. So you have your vertical dynamics defined, and you can build up your first suspension models. After you made your kinematic and compliance tests, we have already a validation loop. Then we can go to the next one, building up a full vehicle model. Full vehicle model can already be used for handling maneuvers like in constant radius, cornering, step steer, ram steer, what else? We can test it, we can simulate it, and also there's a validation loop where we compare this results with something we have measured in reality. After all, you can go directly, for example, in subsystems like the steering system. You are also able, regarding the software environment, that you can optimize your steering system very into detail. This is something else you can directly include in this software environment, not only suspension or axle systems, but also like the steering system or the vertical dynamics, but everything still for the handling. So this is the left side. on the right side, regarding ride and comfort, where it's more important to have something like, what can be, or what does, sorry. So in the ride and comfort, it's more complex. We want to see where do we get accelerations over the frequencies, and there it's very important to have an accurate model, to have a very detailed tire model, like we are talking about very physical models like F-tire or CD tires where we use. We are also implementing flexible bodies, so you have the elastic deformation of your systems, like your links. Also, there's also possible to put or include a body in white as a flexible part. You get all these kinds of torsions, of bendings, and also the frequencies, the eigenfrequencies of the parts included in the model. So you can evaluate the ride and comfort behavior, going also into NVH simulations, for example. This is also be possible after this one. So maybe having another look on this road to the development. So in the concept phase, we start with defining the key performance indicators for our vehicle and defining our target areas, most of the time coming from the benchmark and from experience. So we have, for example, at EDAG, we have our KNC fingerprint, which looks something like that. After we defined our KPIs, the second thing is that we can build up our rigid kinematic model in the multi-body simulation. So this is how it could look like. So we are already able to make the first initial simulations and have a look if we are in target or not with our kinematic and compliance targets. After that, we can implement some elastokinematics like bushing stiffnesses or also flexible bodies in the suspension system. So this is how this would look like, and we can do also the compliance tests with our suspension systems. Next step would be the build-up of a full vehicle model. So we have here a full vehicle model which is already prepared for handling ride and comfort simulations. We have everything included, all subsystems are included. We have a body, we have a steering system, we have a powertrain included, and all things you need. So you are ready to simulate full vehicles. So this is what I was talking about, and by the end you can run these full simulations. For example, as you can see here, over a rough road, just the animation where you can see how the vehicle is behaving, how it is bouncing, for example. Systems like we have probably be developed in MATLAB or Simulink directly in our car maker model, and after all we are able to simulate and to applicate our control systems. So I have also another video from that here. So this is our CityBot. It is an autonomous driving robot with an kind of tractor behind of it, which can transport people. And as you can see here, so this is driving completely autonomous by our own controller here. And regarding that, we also implemented in our CityBot, it has a corner module, so we have four wheels with 4 steering systems. So we are completely, and with this 4 steering systems, we can directly select what each wheel does. So we are able to do, for example, an opposite steering. We can go sideways with the CityBot. We can turn on point. We can do a parallel steering, crossway, and we are also able to do a fail-safe scenario. So all these control systems are implemented, tested, and applied in our IPG car maker. So this was probably what we are, how we develop and how our development process looks like. So maybe 2 examples, as I mentioned before. One is what we are doing is we develop, for example, also new axle concepts. So what we were doing here is that we developed a rear axle concept, a semi-independent suspension with transverse leaf spring and wheel hubs. So this was all done just by virtual development, and after the virtual development was done, we give it to our construction guys, and they made it in the CAD program. We built it up and implemented it in our CityBot. So this is how it looked like. We had first of all our simulation model, where we tested all the kind of all the parameters we would like to know, like how is the behavior of a suspension system during a wheel travel, how is the behavior, how are the key performance indicators looking like, and after all we were able to build up this axle system by our own. And at the end, I would like to also show you something what we are doing in the high performance section. So as example, we were asked from our technical partner SSA Performance. They had high performance street car, and they wanted to improve the bump steer on the rear. So what we were doing, we were first of all measuring the hard points on the real car, getting them and implement them in our simulation model. So we rebuilt this axle system in our simulation and tried to figure out what can we change of the hard points to optimize the bump steer. So the main goal was to keep the camber gain, but reducing the bump steer from the red curve to the blue curve. So this was a project we were able to help our partner just by getting the hard points and implementing them in the simulation, doing the simulations, going back to the track, and after all, SSA Performance gave us the feedback. Well done, the car is much more drivable now. Another thing we have done for SSR Performance is lap time simulation. For that we have used also an IPG car maker model where we did all this kind of parameterization. We implemented all the data we needed to rebuild the vehicle they wanted to have to compare it. We also built up the racetracks by our own. It was, for example, the Hockenheimring, the Red Bull Ring, or the Nürburgring. And we analyzed what parameters are influencing our lap time. Because the main goal was, of course, not just to be as fast as the competitors. Of course, we want to be faster, and what have to be done with the current vehicle they had to improve the lap time. So first of all, I would like to show you a short video, because we have rebuilt a benchmark vehicle in the IPG car maker, and you can see it driving on the left, and on the right it's a video of, you can find in YouTube from the real drive, and if you compare it, it's quite perfectly fitting. So you can see you can see directly how good the behavior of the virtual car is compared to the reality, because it's quite driving the same. So what we have done then was to have a detailed look what can we do to improve the lap time of the car they wanted to modify. So first of all, we tried, for example, for reducing the weight. So we found out about 30 kilograms would be most efficient to gain some lap time. And also, for example, the weight distribution, we modified it, and the weight distribution 39 to 61 was also the best thing for gaining some lap time. So we did a lot of other sensitivities then, and at the end, the conclusion was what we would suggest to SSR, what they have to do to the car, that they are able to gain the lap time and to get the lap time they wanted or they had as goal, and to be faster than the competitors. So first of all, they had to implement the turbo engine, for example, and modify the gearbox. They have to reduce the weight about 30 kilograms, as we have seen in the table before. We also had a detailed look on the aerodynamics, for example, and some other stuffs. So we give a kind of list what should be done to get into their target and achieve their goals. So that's it. So thank you for your attention, and if there are any questions, don't hesitate to ask. Yep.
For the lap time simulation, can you go back to the slide of the lap time simulation, please?
Yep.
It says minus 20 kilogram plus 0.2 seconds. So why would you be slower if you throw 20 kilograms?
Mm-hmm. It was because we removed the weight only in the COG. We didn't have a detailed look where we reduce the weight. And that's why it was about this minus 20 kilograms. We lost some traction on the rear axle. Probably I have to say the behavior of the car wasn't so clear, because we had very lack of data. So probably this could still be a bit wrong, but by the end we saw that, because we would also think reducing more and more weight would make it more and more faster, but we have seen that different weight losses also reduce sometimes the traction of the vehicle and also the potential of the lateral acceleration. Especially if you have not said where do you lose the weight. Do you lose it in the front? Do you lose it in the rear? Do you modify your weight distribution by losing weight somewhere? So that's why this, the minus 20 was getting, or was why we get this delta of plus 0.2 seconds while we were reducing the weight. Yeah?
For the multi-body simulation, is the torsional stiffness of the chassis taken into account, and at what stage?
We probably implement it when we will do some ride and comfort simulations. So where's the step where we implement the torsional and bending stiffness of a body in white. There are two ways to do it. So one we have seen was with a picture with this yellow body in white structure, which is a complete flexible part. So this is one way we can implement it. The negative aspect of that is that you have, this is a very big data, more than 1 gigabyte of one part. So the simulation times goes up a lot. The second idea, or the second way we are able to implement a torsion and a bending stiffness, is just by implementing a kind of, in Adams we said it's a kind of a bushing. So you just give a lookup table or something like that, or it's just an torsional stiffness curve. And you set it most of the time with the center of gravity, so you have a front and a rear vehicle part, or left and right, and in the middle you have this kind of stiffness behavior, so you can include this in your full vehicle simulation. Okay. Any other questions? No? Okay, so thank you very much for your attention.